Welcome to Psydactic. Today is Friday, December 27th, 2024, and I'm your host, Dr. O'Leary. I am now a fully boarded psychiatrist in the National Capital Region, and I am currently in a child and adolescent psychiatry fellowship program. Psydactic is my original podcast, started in December of 2021 as a way for me, as a psychiatry resident at that time, to explore new topics, increase my knowledge of psychiatry and of neuroscience. Nothing I say here is personal medical advice, and everything I say here should be considered my opinion and no one else's or no other thing else's opinion. It has been a few months since my last episode, and this is for a few reasons. First is that I did start a new program in child and adolescent psychiatry, so I have been in transition to a new kind of perspective. And because I'm a slow learner, I had to take a step back from Psydactic. The second reason is that I started a companion podcast called Psydactic Child and Adolescent Psychiatry Edition, or CAPS Edition, which I use to help me dive into topics that the American Board of Psychiatry and Neurology promises will be on my CAPS boards at the end of the program. So if you're interested in human development and behavioral health, you can find the CAPS edition of Psydactic wherever you found Psydactic. And I will also be featuring one of the CAPS episodes in this feed soon, so stay tuned for that. I really hope that today's episode is going to be agonizing for you. And what I mean by that is that you will walk away from this with a better understanding of what a pharmacologist or a doctor means when they say that a medicine is an agonist, or a partial agonist, or an antagonist, or an inverse agonist. While a pharmacological antagonist is not the bad guy, it definitely has a role to play in the story of your brain. So let's get started. To understand agony, we have to understand a few things about how cells, including neurons in your brain, receive and send signals. Now, all cells have molecules on them, big complexes of molecules that are either on the surface of the cell, or they are within the cell itself, or they're on the nucleus of the cell. Somewhere, especially on the edges of the cell, there are big complexes of proteins, and these receive signals from molecules. One of the most common types is a G protein coupled receptor. So it sends signals after it receives a signaling molecule that either activate or shut down various metabolic pathways in the cell. And sometimes this results in DNA transcription. Other receptors might activate things called tyrosine kinases. And these are enzyme complexes. And whenever they get activated, they add a phosphate group to another protein, usually an enzyme, that then activates that protein and results in changes in other cell functions. Finally, you might have signaling molecules that hit things called ion channels. And so this might open up an ion channel, or it could shut down an ion channel. And this can depolarize or hyperpolarize a neuron, for example, and that would cause the neuron to either fire at a reduced rate or at a faster rate. So it's important to note that whether molecules are changing the activity of ion channels or G protein coupled receptors or kinases, the downstream effects of this might actually be to affect a lot of activity in the cell. And it might affect the activity of other receptors, other enzymes, or other ion channels. So it isn't like opening an ion channel will only have effect on that ion channel. It could have effect on G protein coupled receptors or tyrosine kinase receptors. But when I'm talking here about agonists and antagonists, I'm talking about the thing that it binds to. That's what I'm referring to. Not its downstream effects, but what it does to the thing that it's binding to, its effects on how that thing communicates. So whether or not you're an agonist, an inverse agonist, a partial agonist, or an antagonist, you're binding to some sort of signaling complex or ion channel. And that can cause one of kind of four different things. Now, there are more things, but I'm only going to discuss four today because that's all that's super relevant to what I'm talking about. So the first thing that these molecules can do is increase the activity of either the signal or the ion flow on whatever it binds to. So it can increase activity. The second thing it could do is decrease activity of the signal or the ion flow. So there's some level of activity and it's decreasing it. The third thing it could do is actually prevent any changes to the activity of the signal or the ion flow. So there's some base level of activity, and whenever it binds to it, it's going to prevent any changes to that. It's going to keep it where it's at. Now, the fourth thing that these molecules could do is kind of place a new floor and a new ceiling on the signal frequency or the ion flow. So it's going to change the potential cap and the potential bottom out of the activity in either the ion channel or this signaling complex. Now, let's get started trying to tease all of that apart. And I'm going to start with the agonist. Now, you might have heard someone say an agonist activates a receptor, but this is a false definition. A better definition is that an agonist increases the activity of its receptor. The receptor might already be active, but what it's doing is increasing the activity of the receptor, and that's all it's doing. So many signaling pathways, they have this baseline or constituent rate of activity. You'll hear me say that word, constituent rate of activity. The same is true for like enzymatic activity or for ion channels, and agonists increase this activity. Now, full agonists, what we call a full agonist, are molecules that increase the activity to whatever is its natural maximum, its natural limit. So we consider that to be a full agonist. Full agonists that most people know are things like dopamine, norepinephrine, serotonin, melatonin, vasopressin. So these are molecules that your body produces in order to act as full agonists on whatever receptors they hit. Now, to make things more complicated, some of these molecules do agonizing at other places, but they're not full agonists. They're not giving it the full amount of agonizing that it could possibly do. But for the receptors that it is supposed to hit, when it hits those, these are considered full agonists. Doctors also give artificial or pharmacological agonists. For example, we give dopamine agonists like pramipexole and ropinirole to people who have dopamine deficiencies, such as in like Parkinson's disease. And these dopamine agonists serve to replace dopamine as an agonist within the brain. It increases the activity at the receptors that dopamine would have hit as a full agonist. We also have serotonin agonists, such as the triptans. You might have heard of something like sumatriptan. These are given for migraines. And they work by being full agonists at 5-HT, 1B, and 1D receptors. These are serotonin receptors. Because they act as agonists at these receptors, they increase the activity of those receptors. The downstream effect of that is to decrease the intensity or duration of someone's migraine headache. Now we have the full agonists, but we also have something called a partial agonist. And this is one that's kind of difficult for people to understand in the beginning. So a partial agonist acts like an agonist in that it increases the activity of a receptor or an ion channel or that protein kinase. But this increase in activity happens in the absence of the full agonist. But if the full agonist is present, the full agonist cannot agonize that receptor to its potential. So you could say that a partial agonist increases activity at this receptor. But if you add a full agonist, it's going to prevent the receptor from responding fully to that full agonist. So you could say it lowers the ceiling and it increases the floor of activity of that receptor. Some of the most common partial agonists that we know we give on purpose, are antipsychotic medications, aripiprazole, brexpiprazole, cariprazine. And all of these are strong partial agonists at the D2 and even the 5-HT1A receptors. So they're partial agonists of dopamine and a serotonin receptor. What this means is that They don't act to completely block the receptor, but they do reduce some of the activity at that receptor when the body releases dopamine. So they increase the activity at that receptor at baseline. But imagining that we have too much dopamine already to begin with, it's actually going to reduce the real activity of that receptor because it's going to reduce the effects of the full agonist. Another drug called clozapine, and I'm going to mention it multiple times because it has many different mechanisms of action at many different receptors. Clozapine is a strong partial agonist at the M1 or muscarinic 1 receptor, and it's a weak partial agonist at the 5-HT1 receptor. So what this means is that clozapine does a lot of its work, its antipsychotic work, by partially agonizing a muscarinic receptor. Some of you may have heard about LSD, or D-lysergic acid diethylamide. It is a common party drug which also acts as a hallucinogen. And part of its action is by binding to 5-HT1A as a full agonist, but it's a strong partial agonist at 5-HT2A, among other receptors in the brain. So by being a strong agonist at 5-HT2A, it contributes to our tendency to produce intense hallucinations or looseness of associations, or sort of these dissociated experiences that people talk about when they take LSD. All these strange perceptual experiences happen in part because LSD is a partial agonist at the 5-HT2A receptor. Now, when I get to antagonists, we'll talk about how 5-HT2A antagonists can reduce people's tendency to hallucinate or have strange perceptual experiences. And we're not quite there yet, but almost. So I've talked about how full agonists are generally molecules that are produced by the body, such as dopamine or norepinephrine or serotonin. But we also might be able to introduce molecules that act as full agonists, especially like dopamine agonists. Technically, if I were to give a full dopamine agonist, like pramipexole, and then I were to give a partial agonist, like aripiprazole, that full agonist would not be able to exert the effects that it could before, because the partial agonist will be competing for that receptor. And it's going to put a ceiling on how much that the full agonist could stimulate that receptor. But at the same time, it's going to increase the baseline activity at that receptor. So the receptor's activity is going to increase, but it won't be able to increase as much as it could have in the presence of a full agonist. So those are partial agonists. Next, I want to talk about the inverse agonist. And this is probably the one that is the least talked about. Partially because there's few clinical applications where inverse agonists are obviously working. But it's an important concept because it helps you understand the difference between an agonist and an antagonist. And I'll get to an antagonist in a minute. But an inverse agonists work on these molecular complexes like these ion channels and these G-protein coupled receptors by decreasing their baseline or constituent level of activity. So these complexes have some level of activity, and inverse agonists don't block it. They don't necessarily block the change. They actually make the change happen in the opposite direction. So they reduce the activity, or they cause it to do the opposite of what it would have done before. So if a G protein coupled receptor is normally signaling at its baseline rate, an inverse agonist would stabilize it at an even lower rate, or it could shut it off entirely. And that's different than an antagonist, and I'll get to that soon. But antagonists don't shut things off, they just prevent change. But an inverse agonist could shut off a constituently active receptor complex. Hypothetically, inverse agonists could do other cool stuff, like either reduce the baseline rate of flow through an ion channel, so make it less leaky than it already is. Or it could reverse the flow through an ion channel. So an inverse agonist, if it binded to an ion channel, instead of ions flowing in through that channel, they would flow out, or vice versa. You could say the same thing about other kinds of transporters. So serotonin transporter, for instance. An inverse agonist would take a serotonin transporter that's pumping serotonin into a cell and make it pump out of the cell. That would be an inverse agonist. It would also be an inverse agonist if it merely reduced the rate at which the serotonin receptor at baseline pumped serotonin back into the cell. So it would either reverse the flow or simply reduce its constituent activity, and that would make it an inverse agonist. There are not a lot of inverse agonists that are common in clinical practice, at least not a lot that we've identified as inverse agonists. One that is used a lot by internal medicine doctors is called carvedilol, and it's a beta blocker. So it can help a little bit with blood pressure, but mostly it reduces the maximum that your heart is going to pump. It's going to reduce your heart rate. But it does this not only by preventing stimulation of the beta adrenergic receptors, but it actually reduces their baseline activity. So it acts as a weak inverse agonist, not just an antagonist, not just something that stops it from being changed, but something that actually reduces the constituent activity of beta adrenergic receptors. Clozapine, which I said I would mention multiple times, is a 5-HT2A inverse agonist. So I mentioned we have LSD, which is a 5-HT2A partial agonist, a strong partial agonist. So it's going to increase the baseline rate of 5-HT2A. Clozapine will do the opposite. It will reduce the baseline rate of 5-HT2A firing. Now finally, I'm to an antagonist. There's a common misconception that an antagonist is like the opposite of an agonist, that instead of increasing the rate of firing, it reduces the rate of firing. But I just said that an inverse agonist is something that reduces the rate of firing. So what is an antagonist? An antagonist just prevents signaling from being changed. So whatever the baseline constituent rate is, when an antagonist binds to that, that's going to be its rate. It's not going to change. So they prevent agonists and inverse agonists from having any effect on the receptor. They're just basically competitors whose effect is to prevent other molecules from making any changes that they normally would. It does not change the firing rate of the receptor or the rate of flow through like an ion channel. But it prevents the full agonists and the partial agonists and the inverse agonists from having any effect. The most famous antagonists in psychiatry are the dopamine antagonists. And these are a subset of what we call the antipsychotics, or the major tranquilizers. These generally have strong activity at D2 receptors. They antagonize D2 receptors, preventing dopamine from having its normal effect there. So they don't shut them off if they are constituently active, but they prevent dopamine from turning them on. However, antipsychotics are often also antagonists at many serotonin, cholinergic, and muscarinic receptors, and this results in a lot of their side effects. So not only are they preventing changes in the rates of constituent activity in dopamine receptors, they're changing the rates of those in many of the serotonin receptors and the cholinergic receptors and muscarinic receptors. Now, if you want to understand more about how that affects humans, then you can go back to a December 2023 episode that I did, or series of episodes on dopamine that I did, and that will help to explain that. Other drugs that we use that are antagonists, especially that psychiatrists use that are antagonists, are the ones that help people to go to sleep. So drugs such as mirtazapine are strong antagonists at histamine receptors, in addition to many of its other activities. But because it is an antagonist at histamine receptors, people get drowsy and they feel like going to bed. The last thing I'm going to talk about is an inverse antagonist. Just kidding. There's no such thing as an inverse antagonist. There are agonists and inverse agonists, but an inverse antagonist can't really exist. An inverse antagonist would just basically be anything else. It's kind of a redundant term because it would simply be a molecule that made a receptor either function normally again or increase its activity when in the presence of a full agonist or something like that. So it would be a very redundant term. It's not a term that's ever used. There is no such thing as an inverse antagonist. Now, I imagine there could be a class of molecules that would prevent an antagonist from antagonizing a receptor, but then not change the base rate of activity or the activity in the presence of an agonist or inverse agonist. But I'm not sure what you would call that. That would simply be an antagonist of an antagonist. It would be an antagonist blocker, not an inverse antagonist. But maybe I'm not aware that there actually are inverse antagonists, and if you could correct me, you can go to sidactic.com, fill out a form there, and let me know what you know. To wrap up this episode, I want to mention just how complicated our signaling systems actually are. So technically speaking, someone should use the term agonist, antagonist, etc., to refer only to the direct effects of that chemical's binding on whatever complex it's binding to. However, there are downstream effects. So just because something is an antagonist at one receptor doesn't mean that the downstream effects of it binding to that receptor are going to be to reduce something. It might be to increase something. We talk about agonism only with respect to the thing that it binds to. Let me give you a quote from an article in CNS Drugs just to demonstrate how complicated things can get. And it's a quote about mirtazapine. Mirtazapine activates 5-HT1 receptor-mediated serotonergic neurotransmission by enhancing the stimulatory effect of the noradrenergic system on serotonergic cell firing, an alpha-1 adrenoreceptor-mediated effect, as well as antagonizing the inhibitory effect of the noradrenergic system on serotonin release, alpha-2 adrenoceptor-mediated effect. So that's kind of a long and complicated way of saying that it agonizes alpha-1 receptors and antagonizes alpha-2 receptors, but the downstream effect is to change serotonergic signaling. I appreciate your patience waiting for this episode to come out, if you were in fact waiting. In the meantime, if you want to try out Sidactic Child and Adolescent Psychiatry Edition, please feel free. In the future, I also want to feature other podcasters, especially ones in psychiatry, if I can get them on, and introduce you to their work, because over the last 3 or 4 years, there has been an explosion in resources through podcasters that do an absolutely amazing job making topics that, if you're just reading a book or trying to figure it out online, might be too confusing, really accessible to people. But until next time, thank you for listening. I am Dr. O'Leary, and this has been an episode of Sidactic.